Okay, good morning everyone. So I have the auspicious honour of doing the first lecture here today. As you'll see, some of the other speakers that are coming up later on today, we're really surrounded by experts in the field here today, and I'm really looking forward to some of the later talks, and hopefully I can do as good a job as they can and deliver some interesting information to you all. So I'm going to talk a little bit about detergents. Please feel free to interrupt at any stage if I've gone over something too fast, or if there's something that you think I can clarify a little bit more. We've got plenty of time to go through those sort of things. And so detergents are fairly a key property or a key tool, as Daniel mentioned, in the 2D crystallisation of membrane proteins. This is just a bit of an overview of what I'm going to talk about today. So I'm just going to talk a little bit about hydrophobicity, which is basically why we need detergents for 2D crystallisation, and how detergents and membrane proteins come together for structural studies of membrane proteins. I'm going to go into classes of detergents, detergent phase diagrams, and some properties of detergents that are related to this, and properties of detergents which make them useful in the study of membrane proteins for crystallisation. And I'm just going to finish up with some interesting developments on the quantification of detergents and also on the development of some alternative amphipathic compounds. Okay, so hydrophobicity. Basically, the concept of hydrophobicity is based on the fact that water has a very strong hydrogen bonding network. This is the intrinsic property that gives water its character. There's a strong network of hydrogen bonds which allows water to exist the way it is. And hydrophobicity is something that disrupts this network of hydrogen bonds, and it causes changes in entropy and changes in energy to adjust to this disruption. So effectively, as you can see here, it's the strength of the hydrogen bonds in water that gives it its liquid properties, and it's also this strength that gives rise to hydrophobicity and hydrophilicity. So on the left here, we've got an image of a well-ordered hydrogen bonding network within water, and on the right we've got some hydrophobic compounds which have been introduced, and you can see that they disrupt this strong hydrogen bonding network. Okay, so the net effect of this is that when we introduce hydrophobic compounds to water, what happens is that we get a disruption of order within the system. This hydrophobic bonding network is an ordered system. When we introduce a hydrophobic, this water bonding network, hydrogen bonding network, is an ordered system. When we introduce hydrophobic compounds, we get a reduction in order. And so what needs to happen is there needs to be an adjustment to this system. And so what happens is we get order introduced eventually at a high enough concentration into the hydrophobic compounds, and this forms something called a micelle, as you can see with the detergent here. This ordering within the detergent micelle compensates for the disorder within the water when we disrupt the hydrogen bonding network. And so this is the reason really that we have detergents. But before I get onto that, I'll just talk a little bit more about this hydrophobic effect that we have. And it causes these things I've just talked about. So in the case of soluble proteins, this hydrophobic effect is the thing that drives the folding of proteins. We have hydrophobic surfaces and hydrophobic residues in our protein, and these tend to be buried on the inside of the protein. And this is a really strong driving factor in the folding of proteins, along with things like disulfide bond formation and other characteristics. In the case of membrane proteins, however, what happens is that these hydrophobic patches tend to appear on the surface of the protein quite often. And in a native environment, these hydrophobic patches are protected by an amphipathic compound, usually a lipid membrane within our native environment. But what we can do with detergents is that we can actually solubilise these membrane proteins away from their native environment by taking advantage of the fact that detergents are able to shield that hydrophobic domain of the transmembrane protein. Okay, so before I go any further, I'm going to talk a little about solubility and crystallisation and how this relates to hydrophobicity. And in a couple of slides' time, this should all link back together if it hasn't already. So this is a slide that I use to explain my view of how crystallisation works and how we should visualise crystallisation as crystallographers. And this is from a TV show that's called The Price is Right. I know it screens in my home country in Australia. I know it also screens in America here. I'm not sure how far else around the world it's gotten to. But basically this is a game called Cliffhangers. And what happens is we have a guy that starts down the bottom of the mountain, and in the Australian version he has a dog with him. In this version he just yodels on his way up the mountain. And the contestant has to guess the price of 3 prizes. And depending on how far away they are from the price of those prizes, the guy yodels and walks up the mountain for every dollar that he is away. And you have 25 steps on the mountain, and if you can guess the price of your 3 prizes and stay under $25 away from those prices, then you win the grand prize and everyone goes home happy. And this is kind of akin to getting a crystal. So if we can make this guy walk a long way up the side of the mountain here, but not fall over the top, and we've won the jackpot, we've grown our crystal. If we go over the top, we've gone too far. If we haven't gone up far enough, then we don't win either. Okay, so this mountain is kind of akin to a solubility curve. And we have a number of properties which help us achieve this point of crystallisation at the top of the mountain. These properties are things which usually affect solubility. And they're things like we can decrease the solubility of the protein by increasing precipitants, by manipulating pH, by salting out, by changing temperature, and by manipulating things like detergents and lipids. Okay, so this brings us back to detergents. And effectively, detergents are really the single compound that probably had the greatest influence in allowing us to study the structure of membrane proteins. Before detergents, if detergents hadn't have existed, then we would have had no way of enticing membrane proteins out of their native environment, and this would have made them very difficult to study structurally, and indeed it did for a long time. Okay, so the reason for that is shown in a lot of these slides, which represent different forms of membrane protein crystals. We have 3D crystal forms here, showing the membrane protein surrounded by a lipid micelle. We've got stacked 2D layers. We've got typical 2D crystals, which a lot of you will be familiar with. And we've got cubic phase lipids. And all of them involve the transmembrane region of the protein being protected by a detergent micelle or by an antipathic compound of some sort. Okay, and just to relate that back to 3D crystallization, on the left here, we can see an example of a membrane protein, and on the right we can see some soluble proteins. And the link between amphipaths and the approach that's taken with soluble protein crystallization, I guess, is that in the case of membrane proteins, we're using amphipaths to restrict the solubility of our protein. We have control over the solubility of our protein by reducing or increasing the amount of detergent or the amount of lipids that we have within our system. And in a similar way with soluble proteins, usually people will use precipitants such as ammonium sulfate or PEG, which are basically water-drawing molecules which restrict the amount of water that's available to solubilize the protein, and in the same way controlling the solubility of the protein system and moving us up that mountain towards the point of crystallization. Obviously there's a lot of fine-tuning that goes on in this process, but that's basically the general gist of it. Okay, so just to get back to detergents and a bit of a definition of detergents from the textbook if we like. So detergents can basically be defined as antipathic molecules that contain both a polar head group and a hydrophobic region, and this is known as the TAL group. And they usually symbolise something like this. Okay, so these polar head groups are hydrophilic. They love water. They're able to form hydrogen bonds with that water, and they're able to be involved in that hydrogen bonding network. The tails, on the other hand, don't like water. They don't participate in that hydrogen bonding network, and so what happens is that when we get to a high enough concentration of detergent, we get something forming called a micelle. And this involves all the hydrophobic tails of the protein stacking together, protecting them from the hydrophilic surface, and the heads of the detergent interacting with the water. Now, one of the big advantages of detergents that I've already touched on is that they're able to replace lipids in solubilizing membrane proteins. Okay, and so that means that detergents play a really important role in 3 different steps of our studies of membrane proteins and structural studies of membrane proteins in particular. And these steps are shown down the bottom, and I'm going to go into these in a bit more detail now. So basically, detergents are used for the purification of membrane proteins. They're used in the stabilisation of membrane proteins once we purify them away from their native environment. And they're also important in ultimately the crystallisation, where they are usually removed, but the type of detergent used can affect crystallisation. Okay, so to talk about solubilisation. Basically within this leaf here, we've got millions, probably billions of protein molecules. And what we need to do is we need to get those protein molecules out of their native environment so that we can study them at the molecular level. And so the way we go about this is using detergents. So we get into the membrane level, into the cellular level, into the membrane level, and then we solubilise away our protein molecules using detergents. Okay, so this is just an example of some proteins isolated from a photosynthetic complex prep. Okay, and so the types of parameters that are important for detergents that we want to use for protein purification are things like we need pure detergents. We need pure isomeric forms of the detergents, not just pure detergents. Their ability to solubilise away lipids is important, so obviously we want detergents that are good at this point in time at solubilising away the membrane protein from the native lipid environment. But at the same time, we want to be able to protect against denaturation of the protein complex, because if the detergent is so harsh that it just strips away all the lipids and then denatures the protein, then it's not of much use to us. Low concentrations are favourable because this brings down the cost. And the ability to exchange and remove the detergent is obviously also important as well, because ultimately, when we want to grow 2D crystals of our protein, we need to remove that detergent later on. Okay, so this is just another slide showing the purification of photosynthetic complexes, and you can see the effect that different detergents have on isolating different complexes, on denaturing complexes where you've got subunits falling off, and ultimately coming up with different preps. Okay, so sometimes we don't need to go all the way and harshly solubilise away a membrane protein from its native environment. We can actually use detergents just to mildly solubilise away the membranes, and if we're lucky, these membranes will actually contain membrane proteins in 2D ordered arrays that we can study as is, without too much extra effort. And certainly that's the case for protein, the nicotinic acetylcholine receptor, which is one of the first proteins to be studied by 2D crystallography. And so you can see represented schematically here, effectively the way that this research was conducted is by taking a protein in a densely packed array of native membranes, and by using some very fine solubilisation conditions to induce rearrangement of the protein complexes within this membrane, and ultimately come up with a 2D array. So in this particular study, there was no need to completely solubilise away the protein from the native membrane. It was just making use of detergents to gently tweak with the system as it was, and come up with a system that we could study by electron crystallography.
So I guess this is the only time we're actually talking about in vivo crystallization or in situ crystallization. So there's this old technique with phospholipase A2.
Certainly, yes.
So maybe just, I don't know, is anybody using this still? I think the detergent, the solvent detergent extraction is being used quite a bit now. But it's stored with this phospholipase A2, which basically trims off one of the lipid tails. And you end up with a head group with one tail, which is basically also a very mild detergent. And that can dialyze away. And in this way, you can also create 2D crystals. VDAC was done initially like this.
Yeah, that's right. The voltage dependent, yeah.
So you add very tiny amounts of this phospholipase A2, and at the same time, you have to dialyze because you generate these lysophospholipid. And in this way you can also crystallize proteins in the membrane. But both these techniques are actually very hard to reproduce and very difficult. Do you agree?
I would agree with that, yeah. So, yeah, I've actually got another slide in a different talk, but I don't have it in this talk, but basically showing effectively what you were just showing there, what you were talking about there, showing that we can achieve the same effect by basically introducing something which doesn't mildly solubilise away the lipids, but reduces the amount of endogenous lipids in some other way, such as phospholipase A2, which would effectively achieve the same thing. The problem, as Tom mentioned with this, is that it's only really suited to a very small percentage of proteins, and probably these are the proteins that have already been studied. And so, while the low-lying fruit, so to speak, has already been picked in this respect, we've now got to go to more challenging approaches to try and apply these techniques more generally that will work on a wider classes of proteins. Okay, so I've talked about solubilising proteins away from the membrane, but once they're solubilised away, it's important that we're able to keep these in a stable environment prior to doing what it is that we want to do with them downstream. And so detergents are also important, therefore, in stabilising membrane proteins within solution. Without detergents, we would solubilise the protein away from the native membrane, and then the protein would precipitate out due to the high hydrophobic surface area. And so the types of properties that we'd like to have in detergents in this respect is, again, we'd like to have pure detergents, although this is probably not as critical at this point in time. Again, we want to keep an eye on denaturation, so the ability to protect against subunits being dissociated away from our main complex, and indeed to protect against unfolding and denaturation in general, is an important property of detergents at this stage in the procedure. We need to have micelles which are adequate to prevent exposure to the transmembrane domain. So if we've got very small micelles, then these might not cover up a very large transmembrane domain. Again, low CMCs are of interest because this then leads to low concentrations of detergents, and some detergents can be very expensive. And so if we're working at very high concentrations, then this can be very costly. And exchangeability is, again, very important. Okay, so this is a schematic now of us basically getting down to the nuts and bolts of the structural biology of what we want to do, and that is growing 2D crystals of a membrane protein. Okay, and so this can basically be thought of as a reversible process, where we start off with our membrane protein protected in a native membrane or in a reconstituted membrane. And we consider it a reconstituted membrane if we consider it as a reversible process. So we have our transmembrane protein here shown in some sort of lipid membrane. We solubilise away this lipid membrane, and what we get are mixed micelles of protein within a detergent. until we get to single monomers of protein down the bottom here. Then what we need to do is we need to be able to get back to where we started from under some sort of controlled conditions, which are going to induce protein-protein contacts and 2D lattice formation. Okay, and so the way that we need to do this is by some form of detergent removal. And some of the other talks this afternoon are going to focus fairly heavily on that, so I'm not going to talk about that too much today. But there are several techniques, and the most common ones are probably dialysis, hydrophobic beads, and dilution techniques. And so by applying this method of detergent removal, we can move back through this reversible procedure to a situation where hopefully we've got protein-protein contacts forming and 2D crystals forming. Okay, so within this little stage down here, usually we've got a lot of different protein, lipid, detergent, micelle species that exist. And some of these are shown on the right-hand side. So we've got our typical protein detergent micelle where our protein is completely solubilized by detergent. We've probably also got some mixed protein detergent lipid micelles. Maybe something with a bit more lipid. Then we start to get to things like bicelles, which are larger micelles with some sort of liposomal content in them, and detergent solubilized in these. Larger planar lipid liposomes. Small vesicles like this. And of course we can have denatured protein if the detergent's not doing the job that we want it to do. So there's a lot of things going on in this solution here. Okay, and as I showed earlier with the analogy with the Price is Right game show, basically what this is all about is going through this reversible procedure of starting off with a protein in a native membrane, getting to a solubilized protein, getting back to a protein in some sort of membrane, but at the same time tweaking some parameters so that we end up at this point on the solubility curve where we've got at this point here where we've got favourable interactions taking place and we've got 2D crystals forming. Okay, so just to talk briefly about methods of detergent removal, we've got some of them illustrated here, and there are a number. There's things like biobeads, calbiazole, cyclodextran. Dialysis is a good method, and this is an example of microdialysis buttons, and this has probably had the most success so far. And there are also other less common techniques like gel chromatography and ion exchange chromatography. And some of the other speakers will talk about this in more detail later. Okay, so these are the results of a study that was conducted about 18 months ago now, where we looked at about 79 membrane protein structures contained within 140 publications and tried to analyse what detergents were most useful in crystallising membrane proteins. And as you can see here, there are some that crop up quite a lot, but you can also see there's quite a diverse range. And so what this really is telling us is that there's not one universal detergent which is going to be useful for crystallising membrane proteins, and that probably doesn't come as a surprise to a lot of people. But we can interrogate this data further and look for some patterns and try and fine-tune approaches to what detergents we should be using to crystallise membrane proteins.
So wait a second, is this 2D or 3D crystals?
This is 2D crystals, yeah. So something you'll notice here is on the left I've shown detergents that have been used to purify the protein away from the membrane. On the right, detergents that have been used to crystallise the protein. And so what you'll see here is that there's actually slight differences between the two different detergents. And this is quite a common approach that people will exchange the detergent in between the purification and crystallisation step, because as I've highlighted, some properties of detergents that are desirable for purification may not be desirable for crystallisation and vice versa. Okay, so now I'm just going to talk a little bit about the three main classes of detergents that we have available to us. And these really fall into three different categories. We have ionic detergents, we have non-ionic detergents, and we have superionic detergents. So firstly, ionic detergents are things like SDS and CTAB. And these are typically very harsh detergents. They're not used widely for that reason because they tend to lead to denaturation. But nonetheless, they're a class of detergent that's worth mentioning. Related to this is a class of detergents called the bile acid salts, and these are characterised by the fact that they have no clearly defined head group, and so they're kind of a pseudopolar species. Okay, so moving on to non-ionic detergents. And generally speaking, non-ionic detergents are good at breaking lipid-lipid and lipid-protein contacts. Not so good at breaking protein-protein contacts. So this is something that's desirable for us in the study of solubilising membrane proteins away from their native membrane, because they're going to solubilise away from the native membrane, but they're not going to solubilise away multi-subunit complexes. So this is probably the class of detergents that we want to focus on. And some of these detergents include the detergent with polyoxyethylene head groups. This is like the CHE12s, the C4E8s, and these sort of detergents. Triton X100 is also related to these. These are basically polyoxyethylenes that have a aromatic group contained within them. And also the sugar head group detergents, so things like maltosides, glucosides, thiomaltosides, thioglucosides. So these are the ones that crop up a lot. And this is really just included for your notes, but this is a page out of the carbohydrate catalogue which lists a number of those non-ionic detergents. Okay, and then we have sputorionic detergents, and these are detergents which offer the combined properties of ionic and non-ionic detergents in the respect that they have no net charge and they therefore lack conductivity like a non-ionic detergent. But like an ionic detergent, they're good at breaking protein-protein contacts. So probably not that well suited to decrystallization, but maybe in some limited cases where we want to solubilise away and break the protein down into a single homogeneous species. And probably the most commonly known example of sputorionic detergent is chaps. Okay, so to go into non-ionic detergents in more detail, we've got things like alkyl glucosides, alkyl maltosides, and also sucrose-based detergents. Okay, and related to these, we've got derivatives of the glucose detergents. So these are the detergents like the Mega series, which are shown here, and also the Hega series, which is similar to the Mega series but with an extra hydroxyl group on the end.
How people actually use those for crystallization?
Mega and Hega. I'm not sure.
I've never heard of it. So anybody with crystals?
For 3D crystal.
3D crystal. 3D?
Okay, and so lastly, just the cyclic maltoside detergents, which are referred to as cyanals by their trade name. And so the advantage of these is that they offer higher CMC values than the corresponding linear detergent, as you can see in this graph here. Okay, so I'm just going to go quickly through some detergent terminology, I guess, or some important properties of detergents which you may or may not have heard of before and which will probably crop up at some stage in the future. Okay, so this is a phase diagram of detergent. You can see that detergents exist in three distinct phases. One of these is the crystalline phase, one is the detergent micelle phase, and one is the detergent monomer phase. And we've already talked about these two here. So the point in this graph here where the three phases intersect is something that's called the Kraft point. So this is where we have an equilibrium between the crystalline phase of the detergent, the micelle phase of the detergent, and the monomeric phase of the detergent. The critical micelle concentration is probably more well known to most people, and this is of significance because it's the point at which once we increase beyond this concentration, we no longer have monomeric detergent solution, we're starting to form micelles. And micelles are obviously of great use for the solubilisation of proteins. So this is an important characteristic of detergent. The critical micelle temperature in most cases is the same as the Kraft point temperature, and this is basically a point where we start to solubilise crystalline detergent and we get free monomers in solution, and once we've got enough of those free monomers in solution, we start to form micelles, and that's the critical micelle temperature, or the CMT. Okay, the cloud point of a detergent is basically, again, a temperature measurement, and it's a point where the detergent starts to undergo a phase separation. So, and this usually happens with non-ionic detergents. So if we increase the temperature of our detergent solution until we get to a stage where we get phase separation, we get a detergent-rich phase and essentially an aqueous phase. This is when we've reached the cloud point. Okay, and so the use of this potentially is that membrane proteins can be solubilised away from a complex mixture by approaching the cloud point, firstly solubilising the membrane protein below the cloud point, approaching the cloud point, and then we get a preferential association of the membrane protein into the detergent phase and non-membrane proteins in the aqueous phase. Okay, the next point is the aggregation number, and so effectively the aggregation number is the number of molecules that are contained within a micellar unit of a detergent. Okay, so this is on its own effectively a property that can be used to calculate the critical micelle concentration of a protein, of a detergent.
How defined are these aggregation numbers, and do they depend on ionic strength?
The aggregation number is reasonably defined. The critical micelle concentration varies with ionic strength. So effectively, if you measure a critical micelle concentration, if you measure a phase change in the solution and then take the aggregation number, you can work out the critical micelle concentration, which will vary with ionic strength and other parameters as well, like temperature, pH, buffer conditions, and things like that. Okay, so for more information on this sort of stuff here, I've just included this reference down the bottom, which can be sourced from the Calbiochem website. Okay, and so one of the properties which I touched on, which is really important with respect to detergents, is critical micelle concentration. This is really a parameter which is fairly important for us in terms of solubilising membrane proteins away from native membranes. And effectively, we can think of detergents as falling into two categories when it comes to critical micelle concentration. They can be either low CMC or high CMC, and I've included a few common examples just on this slide for reference, and the sort of ballpark figures that we consider as low and high CMC. Okay, measuring the critical micelle concentration is something that can be done by a variety of techniques. Shown here is an example of a surfactant which has had its critical micelle concentration monitored by 3 different techniques, and these are dye solubilization, light scattering, and surface tension. And so you can see where you get an inflection in the curve is indicating, depending on the technique, it's indicating a phase change, and this phase change is associated with the transfer of the critical micelle concentration. So this is the way that the critical micelle concentration can be estimated. But as Tom just mentioned, this is a property that varies quite a bit with respect to ionic strength of solution, with respect to pH, with respect to a lot of different complicating properties. And so it's something that if you want an accurate measurement, you should probably go and determine it using one of these techniques. Now, in terms of CMC, a lot of different properties of detergents have an influence on, or are influenced or have an influence on the detergent depending on CMC. And so we can generalise a few properties about detergents based on their CMC. So if we have low and high CMCs, usually within a certain class of detergents, so within, say, the glucoside class of detergents, for longer CN chains, we'll have a lower CMC, and for shorter alkyl chains, we'll have a higher CMC. In terms of binding to proteins, we tend to get weaker interactions with the high CMC detergents. High CMC detergents are usually milder at membrane protein extraction. Dialysis is easier with high CMC detergents, and the costs are usually more expensive because the CMC is higher, the concentration we require is higher. So you can see that some of these, neither of the two detergents is really ideal, and so what we need to do is come up with some strategies where we can combine the two. Okay, this basically just illustrates what I've just talked about on the previous page with respect to chain length affecting CMC, shown as an example for multisides and for glucosides. And you can see that as we increase the chain length shown on the x-axis, we get a decrease in the critical micelle concentration. Okay, and so the final property that I wanted to touch on is something called the hydrophile-lipophiles balance, or this is abbreviated to HLB. And the HLB is basically a measure of the hydrophobicity of a detergent, or its ability to solubilise a protein away from the membrane. It's usually recorded as a value between 0 and 20, and it's calculated by this formula. And to relate to this 0-20 scale, basically when we approach 0, we're approaching detergents that are most hydrophobic, most harshly solubilising, and therefore run the risk of denaturing our protein. As we approach 20, these are the least hydrophobic detergents, they're the non-denaturing solubilising detergents. Usually we would use something maybe in the range of about 10 to 14 to solubilise a typical membrane protein. For something that's just an extrinsic membrane protein, we might use something closer to about 20. But this varies depending on the protein we're studying. And one example I'm going to show at the moment comes from a study by Brian Berger at the University of Delaware, where he carried out quite a broad range of experiments using a comprehensive set of detergents, and used these detergents to characterise the activity and the stabilisation, the stability rather, of the human adenosine A3 receptor when subjected to solubilisation by a range of different detergents. Okay, so shown on the left here is a selection of activity and selectivity measurements subject to a certain set of criteria which he developed himself, and the detergents that we use to solubilise the membrane protein away. When he tried to correlate these against the length of the carbon chain in the detergent, what he found was that there wasn't really much of a correlation at all to carbon chain length. You can see that we've got high activity in some detergents with short carbon chains, we've got high activity in some detergents with long carbon chains. There's no real correlation between, say, glucosides all having high activity or multisides all having high activity. Again, if you try to correlate this with CMC, you can see that this is a bit of a scatter plot, and there's no direct correlation between CMC and the activity of the isolated membrane protein. But when you put this against the HLB of the detergent, what you find is that there is quite a distinct relationship between the activity of the protein and the HLB of the detergent used to solubilise this protein. And so this is this is quite striking evidence to show that perhaps the HLB plot is maybe the most reliable measure of the ability of the detergent to solubilise a protein away from its membrane. And so you can see in this particular case here, he found that an optimal HLB of about 14 or 15, which corresponds to the undecyl and dodecyl multisides, was best for his protein of interest. Okay, so going back to the detergents which I showed earlier, where we ran a survey of the detergents used that had most success in solubilising and crystallising membrane proteins, you can see that the most commonly used detergents basically lie all over this hydrofolate HLB plot. And so what this probably indicates is that we don't need to focus on a particular area of this HLB plot when we're screening for an optimal detergent, but maybe screen around all of these HLB parameters and then hone in on a particular value once we know which one is optimal. Okay, and so now just to talk about a couple of new classes of antifathic compounds. How many have time?
On the schedule, you have 20 minutes.
Oh, excellent. Well, it's running out of time. Okay, so some new classes of antifathic compounds. So basically,
so you can go back and show the picture of one of my papers that you.
So as I've touched on, basically, we've got a range of different detergents, some of which are suited to solubilisation, some are suited to crystallisation, but none of them are really perfect. Some of them are either going to be too expensive, some are going to be too harshly solubilising but not good enough for crystallisation, and so on. And so there's always going to be the challenge there to try and develop some new detergent-like compounds which are, I guess, perfect in this respect. And so this challenge was first taken up maybe in the early 90s. This is one of the earlier papers where a group tried to develop something called a peptido detergent. And so this is effectively a peptide backbone which contains a hydrophobic face, and that hydrophobic face can effectively shield the hydrophobic domain of the hydrophobic transmembrane domain of the protein, and kind of act as a buffer which will allow the protein to exist in an aqueous phase. And so this was really the first attempt at developing a synthetic detergent, if you like. And the real focus of this was the stabilisation of a membrane protein within an aqueous environment. And so this was good. It didn't necessarily get us closer to structural studies, but it did allow us to isolate membrane proteins. A second class of synthetic detergents, I guess if you like, similar to this, was called the amphifols, and these had a similar sort of strategy involved. They have a hydrophilic and a hydrophobic face. The hydrophobic face attaches to the transmembrane domain of the protein. The hydrophilic face interacts with the water hydrogen bonding network. And these were designed in principle to have favourable transitions for crystallisation, although to my knowledge there's been no high resolution structural data come out of studies using these molecules, and so I think those are still a work in progress at this stage. A slightly different tack is to take a detergent and make it more rigid, I guess. So one of the problems with detergents when it comes to crystallisation is not only that the micelle has a steric hindrance effect on forming crystal-crystal contacts, but also that detergents are quite flexible, and crystals are all about inducing water. So if we could somehow make the detergents more rigid, then maybe this would get us closer to incorporating detergents into a rigid structural body that we could study. And so this class of detergents here, with increased rigidity, are a class of protein that may have a class of detergent rather, that may have some benefit in terms of future structural studies. And finally, this is one of the more recent attempts to generate, and you can see here, to generate a hydrophobic hydrophilic peptide which will shield the transmembrane domain of the protein. Okay, and I'll just finish up with some comments on quantification of detergents. So accurate measurement of detergent concentration is desirable for a number of reasons, and some of these are listed up here. And there's a number of different ways that traditionally people have gone about quantitating detergents within a solution. Things like radio labelling, colorimetric assays, for example, sugar head groups within a detergent, quantitative thin layer chromatography, surface tension measurements. These are all approaches that have been taken in the past.
About this, if I may say just a word about the surface tension, we have a tool in our lab which is really, really efficient and to measure detergent concentration, and which is, I think, most for 2D crystallization. We've been selling 5 of those, and people are pretty happy with their
I think it's on the next slide, actually.
Oh, sorry.
But yeah, and hopefully I do a good job of plugging it for you. But yeah, so these are traditional approaches, and some of the problems with these is that they can be time consuming. They can require a lot of solution in order to measure the detergent concentration. They may not be so accurate, and so these aren't really ideal for transmembrane protein preps, which can be small in amount. They can be unstable if they're sitting around for a long time and things like this. So why the need to quantify detergents? Well, basically, for one reason, proteins are often purified in excess detergent, and is there really a need to use more detergent than we need to? Probably not. Detergents with large micelles are often enriched during protein concentration, particularly during concentration. This leads to uncertain measurements of detergent concentration. High concentrations of detergent can increase crystallization time, especially by methods like dialysis, and oversized micelles can interfere with the formation of crystal contacts. So accurate and efficient use of detergents is really something that's desirable to the 2D crystallographer. And so this is the machine that we just heard about. So this is basically a recent development in 2006 of a machine which measures and quantifies detergent concentration based on the surface tension of a small buffer droplet. So this buffer droplet in the centre of the machine here is about 20 microlitres in size. It sits on a drop of parafilm, and basically the detergent concentration is estimated or measured by comparison to a standard curve, and this standard curve makes use of the contact angle of the buffer droplet with the surface of the Teflon, and also the overall volume of the buffer droplet. Okay, so the principle involves putting the droplet on parafilm. Detergent molecules at the surface are less energetically favourable than those in the interior, and so what happens is you get a change in the surface tension depending on the free monomer concentration of detergent in solution. And as that surface tension changes, you can monitor the change in detergent concentration based on comparison to a standard curve. Okay, and this is just an example cited in the paper for dodecyl multicide. And so you can see for a buffer droplet of water, we have quite a round droplet. As we increase the concentration of detergent, the surface tension is broken, and you get an elliptical shape forming as you increase that detergent monomer concentration until you get to the extreme event here. And by modelling this, taking images with the camera, modelling this against the standard curve, we can get quite an accurate measure of detergent concentration in a very short period of time using a very small amount of buffer. Okay, so I'm going to finish up there. So in summary, I've talked a little bit about detergents. I've hopefully given you an introduction to this. And hopefully some of the things you can take home from this is that the choice of detergent is obviously a critical determinant of success in membrane protein crystallization trials. Predicting that success is not necessarily so easy, but it's clear to see that the type of detergent certainly has an influence on 2D crystal formation. So detergents influence the solubilization of the protein, the stability of the extracted protein, and ultimately reconstitution into a 2D array. These are the three areas of 2D crystallization where detergents are important. It's difficult to predict which detergent will be best for your protein, and perhaps a broad screening approach, sampling a wide range of parameters, is the best way to go, and then honing in on the particular class of detergents or the particular HLB value, for example, which is best suited to your protein. And this would probably be a reasonable strategy, sampling detergents covering a range of biophysical properties. Accurate detergent quantitation obviously has its benefits in avoiding things like excessive detergent solubilization, denaturation, and extended crystallization times, and maintaining consistency across preps. And there is research going on. There's obviously a niche there for the development of a perfect synthetic novel amphipathic compound which can be used for 2D crystallization. So that's all from me.